So today we're going to be looking at sections 1.4 and 1.5. And 1.4 is inductive reasoning, and 1.5 is a conditional statements. So what are these things? Inductive reasoning. It's a type of reasoning that reaches conclusions based on a pattern of specific examples or past events. This is literally what we did when we were looking for patterns and rules in sequences. Okay? You looked at a pattern in a table, you look for a pattern. From the pattern, we can predict the next events and stuff like that, the next thing that happen. This is what we use when we found the next numbers in a sequence and to write explicit rules. A conjecture is an unproven statement or rule that is based on inductive reasoning. So, inductive reasoning is when we found the next numbers in a sequence, and when you found the explicit rule, that was your conjecture. Now, it was a rule that worked for the numbers we had. See, in mathematics, you have to prove it would have worked for every single number in the entire sequence. And so that requires a little bit more advanced mathematical training to do something like that. So that's why you were doing an unproven rule. We knew it worked, but it was unproven. So that's really what the conjecture was. It's an unproven statement or rule. So the explicit rule was the conjecture. And when you found the next numbers in a sequence or the pattern, that was inductive reasoning. Okay? And so it's basically saying the same thing what it is. We found out the explicit rule for a table and a sequence, and we were writing the conjecture. So I'm going to do an example here to kind of show you and go back to what we were doing before. So this is what we're talking about right here. So here is an example of something that we've done in the past, but also we're going to use here so you understand. So we're going to use inductive reasoning to determine the next two numbers in this pattern. Okay? Based off of what we see, can we predict what the next ones are? And we can do this a couple of different ways. Most of the time what we've done is we did this in a table. So if I make a table, n is the number of terms, term number is n, and then it's a sequence, and so we just use the number of dots, and we call it a sub n. Okay? Being consistent with what we did in the past. So in term number 1, we have 1 dot. In term number 2, we have 3. In term number 3, we have, and you count them out here, so we have 3 plus 3 more, it's going to be 6. And then 4, if you look at it, those dots right there are sitting right there, so we're just literally adding 4 again. So this is the pattern we're noticing. I can say, oh, to get to the next one, just add the previous one, right? So 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10. So the previous answer plus the next term gives me the next number. So with that being said, then I can predict what the next one is by taking the 10 dots from 4 and adding 5 more to it. So this should be 15. And then to get to 6, take the 15 dots and add 6 more, because you're just adding another row equivalent to the number of dots based off of the term number. So this would be 21. And you can keep on going using this pattern recognition, this inductive reasoning to determine the next numbers that we have. Okay? So now what we want to do, though, is we want to write a conjecture. Can we find a conjecture or a rule or a statement that tells me how to find the number of dots no matter where I am? So instead of having to go, let's say I wanted to find out how many dots were on the 100th term. I don't have to go all the way up to 100 to find it. I want to be able to go right to it and figure that out. And that's what the conjecture is. It's the rule that you would find from this. Okay? So we go through this process right here. We look at different kind of things. Is there a way I can figure this out? Is there a pattern that I can notice? Can I get out here somewhere as I keep on going some n value, and can I find a sub n? If I have an n, what would be the number of dots it's going to be? Can I figure out this pattern? And for the most part, you just got to work this thing out, and we would do all of our techniques that we had before. We know that this right here, we do the differences to kind of see what kind of rule we might occur. From here to here is +2, then +3, 4, 5, 6. And then if I do it again, they're all ones. So I know that my answer will be quadratic. So I know that this rule is a quadratic because the second differences are constant. So that means I have to do a product of different terms. So trying different things, usually what I do is I start looking up here. What happens? I just pick two random ones. What happens if I multiply those two numbers together? Well, then I get 20. Well, that can be that times that is 20 and add 5, or subtract 5. Let's try it here. If I multiply those, I get 30. If I subtract 5, do I get 21? No. Well, then I notice, well, 4 times 5 is 20, and that's a 10. So I can just take that 20 and divide by 2, and I get 10. Let's try that. Let's multiply those two numbers. Well, that's 30. If I cut that in half, I get 15. Oh, that's interesting. Multiply those two numbers, I get 12. Cut that in half, I get 6. And so how do I get the next number? How do I get the answer, let's say to 5? How do I get that? Well, I have to have the number that it's on, and then I multiply it to the next number up. So if this is n, then the next number up would be n plus 1. Take that number and then the next number higher, and then divide it all by 2. And that gives me the one I want for n. And that is your conjecture right there. Okay? Triangular numbers. So that's what we were doing. So let's look at some other things that are happening here. Some things to remember about conjectures. For a conjecture to be true, it must be true for every possible case. This involves writing a proof. Okay? To do that, you'd have to do a proof. And most of these proofs are a little bit hard, like the one we just did, the triangular numbers. To prove that is true for all possible cases requires, like I said, a technique that's beyond the scope of our class at this time. But this is the key part right here. To show that a conjecture is false, you only need to show what's called a counterexample. I only need one time where it doesn't work, and then it doesn't work. You can't count it as being true. It may work for all 99 times, but if it doesn't work for that 100th time, it doesn't work. You cannot count it as a true conjecture. Okay, so a counterexample is an example that shows a statement or conjecture is false. So here's an example. Can we find a counterexample to the statement, a trapezoid cannot have more than one right angle? Okay. A trapezoid cannot have more than one right angle. So to find a counterexample is, can I find a trapezoid that has more than one right angle? So you need to understand that, some characteristics of what a trapezoid is to be able to answer this. And so in the course of time, if you don't know some characteristics of a trapezoid, I will tell you right now, but you want to make sure you write these things down as you experience them. Every definition that you come across is something or a tool that will help you answer questions at a later date. So what do I know about the characteristics of a trapezoid? It has 4 sides. One pair of opposite sides are parallel. Okay, that's what the key is for a trapezoid. It's got to have 4 sides, and one set of sides must be parallel to each other. And so try and draw this out. And so here's the sides that are parallel. I just drew a third side here. I try to draw them both right angles. That means they're going to form a 90-degree angle here, there. And then just one side is shorter than the other one. That's fine. See, this side is not parallel to this one, so it's not a rectangle. So this is what a trapezoid looks like. So I have found a counterexample. This is a trapezoid that has 2 right angles, countering this claim. So this claim is false. That's how counterexamples work and what their purpose is. Okay. You'll come across statements that are sometimes they're true. You'll find some that are false. You need to be able to identify the false ones as they come up. So that's our inductive reasoning and counterexamples. Okay. So what is conditional statements? This is now from 1.5 stuff. What is a conditional statement? It's an if-then statement. So that relates a hypothesis, the part that follows the if, to a conclusion that follows the then. They show cause and effect. If this is true, then this is true. If this is false, then this is false. These kind of things. Okay, cause and effect. Conditional statements can either be true or false. A counterexample will show that it is false. Okay, and so here's an example. If a polygon is a triangle, then it has 3 sides. Well, that's true. If a polygon has 4 sides, then it is a rectangle. So these are conditional statements. If this, then this. This is true. If I have a triangle, I do have indeed 3 sides. There is no triangles that don't have 3 sides. If I have a polygon and it has 4 sides, then it is a rectangle. That is false. So I need a counterexample to prove that it is false. And so you just need to find a 4-sided shape that is not a rectangle. Well, we got one sitting right there. Okay, here are some other ones. I can draw a parallelogram. Parallelograms are not rectangles. This is called a kite. It's a 4-sided shape that is not a rectangle. And here's a trapezoid, the one we had above. That is also not. There are other examples that are not rectangles, but here's 3 examples. So I gave you 3 counterexamples instead of just, you only need one to show it's false. Okay, so that's conditional statements. Here's how these kind of break down with different kinds. So, and some notation that they use to indicate it. Related conditional statements. I'm going to let this letter P represent the hypothesis. So remember, the hypothesis is the part that follows if, and then the conclusion, Q. Okay, that's the part that follows then. If you see this symbol right here, this little tilde again, in this world of mathematics, although it's supposed to mean similarity when I talk about objects in statements, it means the word not. Okay, it's called the negation. It means not something. So here are some other ones besides a conditional statement. You have these kind of things. And here's the relationship between them. Conditional statement using P and Q would be this and then an arrow pointing to Q. It means P implies Q. It means if P, then Q. So when you see these symbols, this is what it means. Then you have what's called the converse statement. The converse flips the conclusion with the hypothesis, and then it says, well, then if Q, then P. If Q, then P. That's what the converse statement means. Negation, if I put a little tilde in front of the P, then it means not P. So it means the opposite of whatever P said. Inverse. The inverse statement takes the original conditional and just makes it the negative of it. So if the original is if P, then Q, then this means if not P, then not Q. That's what the inverse is. You just negate the 2 parts. And then the contrapositive negates the converse. If not Q, then not P. So those are the different ones that they're going to talk about. And you're going to be asked to write these different statements when you're given a statement. So here it is, and I'll show you this one. So write the converse, the inverse, and contrapositive for this statement. If a polygon is a quadrilateral, then it has 4 sides. So when you do these different things, you may need to put words in or rearrange the words so it makes grammatical sense. So don't just kind of like swap out stuff, but make sure it makes sense when you're reading it, okay? So this is the conditional statement. That's this part up here. The P then would be the polygon is a quadrilateral, or is a quadrilateral. And then the Q would be has 4 sides. Okay? So what is the converse? So the converse is you flip the then with the if. So again, notice if a polygon. So that will stay because it's the same no matter which way I look at this. So, but here has four sides became the if part now. If a polygon has four sides, then it is a quadrilateral. That's converse. Okay. The inverse. The inverse, again, is the opposite or negates the converse. Okay. I'm sorry, it negates the conditional. So we're just going to put the word not in there. If a polygon is not a quadrilateral, see we just put not in this one, then it does not have four sides. Okay. The inverse. The contrapositive just takes the converse and puts the not in. If a polygon does not have four sides, then it is not a quadrilateral. You just have to keep them straight in your head, which one is which. It's not that hard to write these things out, but you want to be able to, this is all about making an argument, making a case, okay? And so if I know this, then I have that. That's the cause and effect part of mathematics that we're looking at. This is not a very large part of what we do, but it is part of the idea of what we do. The next one we come across is this thing called a biconditional. A biconditional usually is reserved for those ones that work where both things are true or false. It's the combination of a conditional statement and its converse at the same time. And we designate it as not with an if and then, but with an if and only if statement. And then all the conditional statements have arrows. So when you put them both together, you have a double arrow. So this symbol right here indicates that this is a biconditional, and it represents this right here. P is going to happen if and only if Q happens. P is true if and only if Q is true. P is false if and only if Q is false. That kind of a thing. And this is usually used like definitions are usually can be written as a biconditional statement. Some definitions, I should say. And some theorems are biconditional. So here is a conditional and its converse. If a polygon is a triangle, then it has exactly three sides. The converse, if a polygon has exactly three sides, then it is a triangle. So I can combine those into a single statement called biconditional and write it in this fashion. A polygon is a triangle if and only if it has exactly three sides. So it's a little bit more powerful statement in that sense. So in this section right here, 1.5, you're going to be asked to go through and write different statements based off of what they have. Okay, and in the previous one, we're going to be looking at writing using inductive reasoning to find patterns, writing conjectures of those patterns, using counterexamples to help us determine when some statement is false. And then here's a different way to write a bunch of different statements that I can then determine if it's true or false as needed. Okay, so the main thing here is a lot of if-then statements occur because a lot of theorems are if-then statements. If this happens, then that. Even the Pythagorean theorem, okay, it was in a right triangle. Well, it's more like if I have a right triangle, then a squared plus b squared equals c squared. See, it's a conditional statement. Most theorems are conditional statements that were then proven to be true. Okay, so that ends this video right here. We'll do a bunch of examples in class. And so there we go.